everyone, and welcome back. In this video, we are going to implement a stack abstract data type as a singly linked list. So in a previous video, we derived these notes here where we were talking about what a stack is, why is it called a LIFO, last in, first out data structure, what are the types of values and operations that stack ADTs have. So the operations, the 6 most common ones are push, pop, peek, isEmpty, size, and clear. So I want to implement these operations using a linked list. So let's head over to the code and see where we're going to start. Here I've got a linked list class. You can see it has a node struct that stores an integer value, and it has a next pointer to the next node in the list. So this is the singly linked list implementation of a linked list that we derived in previous videos. I just copied it over. I didn't make any changes. You can see here's the common linked list operations that we coded up in linkedlist.cpp. And then main just has a bunch of commented out testing code for all those different operations that we wrote. So here's what we're going to do. We're going to define a stack class. And we're going to define our stack class to extend or inherit from the linked list class. There's two main ways to think about creating a stack from a linked list, and that is composition, a stack has a linked list, or inheritance, which is stack is a linked list, and we're going to go with the latter here, stack is a linked list. All right, so I'm going to open up a stack.h and a stack.cpp in my little text editor here. Let me get some boilerplate header file guard code coded up here, and then we will start with our stack class. All right, so two ways to think about implementing a stack. So the first one is composition. So stack has a linked list. Okay, so it would have an attribute that is of type linked list. Secondly is with inheritance. So stack is a linked list. So with inheritance, we would inherit all of those operations that we defined in linked list, such as add to front and delete at front, which are two really useful operations for our pushing and popping. So we're going to go with inheritance in this video because a stack is a linked list. Okay, a stack ADT is like an abstract representation of a linked list with some constrained operations. So that's the approach that we're going to take here. But there's nothing wrong with doing a composition approach. You just have to manage an extra attribute, which is the linked list itself. All right, so to do option number one, or excuse me, to do option number two, we're going to have to create an inheritance relationship between stack and linked list. So that little bit of code there will create that relationship. So next what we're going to do is define any attributes that the stack class may have, and it doesn't actually have any stack specific attributes. So no stack specific state or data needs to be stored. That's truly how much stack is a linked list. It doesn't need to store any additional information of its own. So now let's think about our stack specific operations. So we're going to have a void push that's going to push an integer onto our stack. And the reason why I'm working with integers here is because our linked list, its nodes store integer values. So I'm just kind of keeping with the code we already wrote for simplicity. We're going to be able to pop an item from the top of the stack, which will be like the head of our linked list. Next, we're going to be able to peek and look at the item at the top of the stack or the head of our linked list. Next operations that we talked about in our notes in the last video is empty, size, and clear. So bool is empty, true or false if the stack is empty or not. And then void clear, which will clear out the list. And then lastly, we'll do int size, which will return the number of elements in the linked list. All right, so I'm going to just copy these and then head over to our stack.cpp file in order to start implementing the bodies of these member functions. All right, so for all of these, I'm going to add stack and the scope resolution operator to make them member functions of the stack class. All right, so let's think about pushing onto our stack when our stack is implemented as a singly linked list. So the key here is the head of the linked list is going to be our top of the stack. So if you return to the drawings that I did in one of our previous videos, you'll see that I always kind of drew the stack in terms of being vertical, right? But when we think about our list and our linked list, we always think about them as being horizontal. So you can draw it either way, but just for helping you visualize what's going on here, I'll make another drawing down here. And I'll say our top of our stack, aka the head of our linked list, is going to point to, say, the beginning of a horizontal stack, okay? And notice that over here in my vertical stack, I kind of had a bottom to it. There isn't really a bottom to a dynamic stack that's implemented out of the linked list, right? There's the last node in the linked list, sure, but it could grow and grow and grow in size, right? Until the system really doesn't have any more memory to be allocated to create nodes. So I'm not going to draw kind of an end to this little container here because, I mean, it can just keep growing and growing and growing in size. Okay, so here's the key part right here, which is our top of our stack is really the head of our linked list. So when we do things like, say, push, what we're really doing is adding to the front or adding to the head of our linked list. And when we do things like popping, what we're really doing is deleting at front or deleting at head of our linked list. That's why inheritance is such a logical implementation for our stack, is because we've already written these functions right here. We already wrote those. All right, so hopefully that kind of horizontal diagram of our stack helps you visualize what we're about to do. All right, so for pushing onto the stack, we're just going to call insert at front and pass along our new item to be added. Let me show you our implementation of insert at front. Here's insert at front. It makes a new node for our new value or our new item to add into the linked list. It checks to make sure the head is null, and if it is, then our head just points to a new node, and it checks to make sure if our head is not null, that means the list isn't empty, and it updates the pointer for our new node to be the current head of the list, and then makes our new node the new head of the list. All right, back to our stack.cpp. All right, so now for our popping, okay, so this is going to be removing items from the top of our stack, which is the head of our list. We are simply going to return whatever delete at front returns. So let me show you delete at front because we actually do have to make a little update to it. So delete at front doesn't actually return the value in the node at the head of the list that's being deleted. So I just added a little bit of code here to save the value in the node to delete, and then return it. And I'm going to use -1 just as kind of a dummy value to denote, say, failure. Like if in fact head is null, there isn't a value to be retrieved from the first node in the list. So this is going to return -1. So just keep that in mind, that there is an assumption right now that -1 isn't a valid value for our linked list or for our queue. All right, and let me show you that I did update that return type for delete at front right there. So we're just going to propagate back that value that was deleted, and it will actually be deleted. There was a call there to the delete keyword in order to properly free that memory used by the node. All right, next we're going to do peek. So peek is just going to look at the first item in the stack, or the first item on the top of the stack. So what we're going to do is we're going to check to make sure that our head is not null. And if our head is not null, then we can simply return its value. And what happens if our head is null? Once again, I'm just going to return -1 to denote failure. So I have to keep that in mind, that I'm using -1 to denote failure. All right, so can we access head directly here in the stack class? Unfortunately, as is, we cannot, because head in linkedlist.h is actually private. Okay, so in order to make head accessible, I could do one of two things. I could change private to protected. Then I could access it from a derived class, or I could add a public getter. So I'm just going to make this protected because I'm thinking my linked list class here is really just to serve my stack class. So I'll be very conscientious of not corrupting the state of my head pointer in my stack class. Okay, so changing this from private to public, now in my derived classes of linked list, I can access the head pointer. All right, next up is isEmpty. So the implementation of isEmpty is actually fairly similar to peek, but instead of returning an integer value or whatever type the value is in our nodes, we're going to return true or false. So if head is not equal to null, then that means the list is not empty, so I'll return false. If I get here, that means that head is equal to null, the stack is empty, I'll return true. All right, now for clear, let's think about what clear does. So clear is going to return the state of the stack to empty, which means that it's going to delete all of the nodes in the linked list. So I want to emphasize that there are two ways to, well, there's more than two ways to do anything. Two main ways to implement clear. So the first is going to be, we can write a loop right here, something like while not is empty. We can pop the stack, something like this. Pop is going to call our delete at front. Delete at front is implemented in linked list such that it will properly update the head pointer, and it will delete, meaning free, the memory used for the node. So this would work just fine. The second option is we can leverage the destructor code we already wrote in linked list. And so I'm going to go with option number 2 because, I mean, I already did option number 1, so might as well, for good practice, do option number 2. And option number 2 is truly more of an inheritance reuse kind of approach. So that means I'm actually going to get rid of clear for now. I'll come back to it in a second. I'm going to head over to linkedlist.cpp and show you the destructor code that we wrote. So the destructor code walks through each node in the linked list, and it deletes the node so that it properly frees the memory. So I can just cut this whole thing and say make another member function actually called destroy list. So now my destructor is simply going to call destroy list. Destroy list, I need a prototype for it, so I'm going to head over to linklist.h. And I have a choice here. I could make it protected, I could make it private, or I can make it public. So if I make it private, then only the linked list class can call destroy list, which currently is all that's happening, right? The destructor of linked list is calling destroy list. Or I can make it protected so that it could also be called from a subclass, say stack, right here, I could call destroy list. Or the last option is to make it public, and then it could be called from anywhere. So because all of my common linked list operations are already public, I'm just going to put this destroy list in here at the bottom as public. That way, if there's some client or some other code that's using linked list, it too could force a clear or a destroy of the linked list. All right, so here's destroy list. Okay, the only thing that we want to make sure of now that it's outside of our linked list destructor is that we set our head to null for good practice. Because now this method, this member function, might be called not when the linked list object is being destroyed, but perhaps in the middle of its life in order to clear out the linked list. So we need to update head to null so that we can't accidentally use a bad memory address that's already been deleted, right? And this test for head equal to null, for example, is pretty ubiquitous in our code. So we want to make sure that if someone destroys the list in the middle of the life of an object, then we're still going to have bug-free code in the rest of our member functions. Okay, so destroy list, just to recap, is now a public member function of our linked list class, and we updated it so that it could be called publicly and it wouldn't destroy the state of our head pointer. So now over here in stack.cpp, I feel more comfortable uncommenting our clear and simply calling destroy list. That's it. All right, our last one here is size. Okay, so once again, I'm going to kind of talk about two ways to implement our size. And so the first one would be to traverse the list and count the number of nodes. Okay, so this is going to be a big O of n, a linear time complexity algorithm. And then the second approach is going to be to add a, say, count or size attribute to linked list or to stack. Make sure we keep it up to date. Okay, so when do we need to keep it up to date? On push and on pop. Or if we were to do this in the linked list class, which is what I would recommend, then on all adds and on all deletes. We would have to plus plus on adds and inserts. We'd have to minus minus on deletes. Or we'd have to plus plus on a push and minus minus on a pop on this kind of int count attribute. Okay, so this is obviously a more efficient approach because it is going to be linear, it's going to be constant time complexity. In order to figure out the size of the stack, we don't need to traverse the linked list. We can just query that attribute value. So I'm going to go with option number 1, but I do just want to emphasize that if your application requires that you query the size of the stack frequently, I highly recommend that you add this count attribute or size attribute to linked list. Okay, I say do it in linked list, not in stack, because linked list has quite a few other, say, append node, insert in order, delete at end, delete node operations that while our stack subclass aren't calling, some other, say, subclass of stack might, unless we were to lock this down or delete these operations that our stack class doesn't use. Okay, back in our size here, so I'm just gonna have an int count is 0, and then I'm gonna need a node pointer called cur_node, which will start at head. We're gonna just traverse the list. While cur_node is not equal to null, we'll simply add 1 to our count. And of course, we'll have our progress towards our Boolean condition being false, which is just advancing our cur_node to its next pointer. After this, we should have our size in count, which we will return. And remember, the only reason we're able to access head here is because in our linked list.h, we did change head to be protected, which means accessible from subclasses. All right. So there's our implementation of our 6 common stack ADT operations using a singly linked list and inheritance. So I'm going to come over here and compile this sucker. And right now it's not going to do anything stack related, but just make sure it still runs. So over here in main.cpp, I'm now going to include my stack.h. And I think I will just comment out all of the linked list specific code here and start with some stack testing code. Okay, so because I didn't actually implement a DVC for my stack, so this is going to invoke the default DVC, the one that really does nothing to initialize any of our attributes of our class. So invoke the default DVC of stack, which will invoke the DVC of linked list. So this is kind of important to know that with inheritance, your superclass or your base class constructors will execute before your subclass constructors. And then for a destructor, it's actually the opposite. So when, say, stack is going to be deallocated, stack's destructor will execute before linked list's destructor will execute. So just something important to keep in mind there when working with inheritance and constructors and destructors in any dynamically allocated memory that you may have. Okay, so let's do stack.push and let's push, let's say 5. And then let's just exercise, let's do one more. Let's do stack.push 3. So 3 should be the top of the stack. So let's see out stack.peak. Let's see out stack.isEmpty. Let's see out stack.size. And then I'm going to probably, let's do this. Let's pop off the stack. So we're going to pop that 3 off. Let's see out the value. And then I'm going to just copy this down here again. Maybe I'll put a nice little label in here. Just trying to make sure that we exercise a lot of our stack operations. Okay, and then I'm going to do this again, pop one more time, and make sure that we're popping off the first value that we put in, which was 5, and then the list should be empty. So stack is empty will return true. All right, so we do 2 pushes. We push 5 and then we push 3. So let me draw what this looks like here. All right, so we initially push 5 and then we push 3. So the top of the stack is 3. Okay, so that's why we see when we peak, we see 3. isEmpty is false. It's not empty. There's 2 items in our stack, and there we see 2. Then we pop, we print out the value we pop, Okay, so we're gonna pop the 3 out. So it is now gone. The top of our stack is 5. Okay, so that's when we peek, we see the 5. IsEmpty is false. There's still 1 item in the stack. And then 1 right here is the size. And then we pop 1 more time. What do we pop off? We pop off the top of our stack, which is 5. Now our stack is empty. Okay, so -1 is returned for peek, which means failure to find something in our stack. And then isEmpty is 1 because now the stack is empty, and size is 0. So the next thing that we should test is our clear. That's the only thing that we haven't tested yet. So I'm gonna put pushing and clearing. And let's just push those 2 items back on the stack. Okay, and then I am going to not pop anymore. Instead, I'm going to do a stack.clear, which we know is going to invoke our destroy list. All right, pushing and clearing, we can see that when we peek, we see -1 because we cleared out the list. So there isn't actually anything on the top of the stack. That looks good. IsEmpty returns 1, which is true. And size is 0, which is in fact the size of our empty list. So it looks like our clear works. What we should also do is a little bit of val grinding here to check, make sure we don't have any memory leaks. Okay, so we run it, heap summary, in use 0 byte, 0 blocks. Okay, all heap blocks were freed, no leaks are possible. All right, awesome. So it looks like we properly implemented our 6 basic stack operations as part of the stack ADT, abstract data type. Thanks for watching, and hopefully you learned a lot in this video. Some fun variations to think about for our stack would be templating it so that it could work with, say, strings or custom objects beyond just integers. And also thinking about that -1. What would be a better approach instead of saying, okay, -1 represents, say, failure or something like that? What would be a better way to implement that? All right, that's it. Once again, thank you for watching.